Good morning, gentlemen. Today is Friday, June the 5th, and today we are going to talk about time dilation in terms of space travel and what Einstein referred to as the twin paradox. Now, yesterday, or in the last lesson, we talked about the idea of an object um, moving through space, and the fact that the faster you move, the more time becomes dilated. And so, what we're going to do here is we're going to take two identical twins, and at a certain point, they're going to be standing on the Earth. Then one of the twins is going to get into a spaceship and take a high-speed journey into space and then return. Now, in this case, it'll be a relatively long journey. And when the spacefaring twin arrives back on Earth, he will find that his twin is now actually older than he is. All right. The twin on Earth will age more than the twin who was in the spaceship because time slows down for the astronaut, all right, the one that's in the spaceship. So if one identical twin takes a high-speed journey into space and back, he will find when he returns that his twin has aged more than he has. Now, let's let's take a few examples and look at how this time dilation actually works, okay? Now, the diagrams that I'm about to show you from this point forward are right out of your textbook. I scanned them into the computer, and so here they are. And they're fairly helpful, I think. All right, so with the twin paradox, we're going to approach this. We're going to take two identical twins. We're going to place one twin in a spaceship and another one and leave the other one on the Earth. Now, the spaceship has to be traveling at a speed near the speed of light, maybe 3/4 of the speed of light or so, in order for there to be a significant difference in the time that we see. So we're talking about, about 0.75 of c, the 3.00 times 10 to the 8th meters per second. All right, and in the end, once we've got the spaceship out in space, it's going to send flashes of light from his ship back to the Earth every 6 minutes. So according to the astronaut, he's setting off his spotlight or whatever it is every 6 minutes. Okay, is that clear? All right, so the guy on Earth is just sitting there with his telescope, looking up into the sky. The spaceship is moving away from the Earth. Well, we'll see what the spaceship does. We'll talk about that in a minute. But the guy on the ship, the astronaut, is sending a beam of light back to the Earth every 6 minutes. So how does this actually work? All right, well, in the first case, what happens is we'll start with the spaceship just sitting in outer space. It's not moving. It's not doing anything else. All right. The only thing that it's doing is sending a flash of light from a big spotlight or whatever it is every 6 minutes. And so the twin who's still on Earth is going to obviously see a flash of light every 6 minutes. Okay. So when no motion is involved at all, the light flashes are received as frequently as the spaceship sends them. So there's no difference here because the ship is at rest relative to the Earth. And so if it sends a beam of light every 6 minutes, the twin on Earth will see a flash of light through his telescope every 6 minutes. That's easy peasy, right? It'd be the same thing if you were sending, flashes of light from your bedroom window out to your neighbor's bedroom window every 6 minutes. Your neighbor would see it every 6 minutes. Same deal. All right. No matter how far away the rocket ship is, that beam of light will still reach the flashes of light will still be seen on Earth every 6 minutes. Now, it changes, however, when the spaceship is in motion, right? In this scenario, we're going to have the spaceship actually moving toward Earth at a very rapid speed, all right? So the ship is now moving very quickly back toward the Earth. Ooh, that diagram is a little bit blurry, but again, the spaceship is still flashing the light every 6 minutes. But because it's moving so fast, it's actually catching up with the beams of light, the flashes of light. And so what happens is that the guy on Earth, the twin on Earth, is going to actually see flashes every 3 minutes. All right. Now, this is an estimate, of course, and just an example. That determination would be made by how fast the ship is moving toward the Earth. But let's say the guy on Earth is now seeing the flashes every 3 minutes, all right, even though the astronaut is sending them every 6. So when the ship moves toward the Earth, the flashes are spaced closer together and they're seen more frequently. Okay. On the other hand, now we're going to have the spaceship moving away from the Earth. And so in this case, the rocket ship is moving away from the Earth, but it's still sending flashes of light every 6 minutes. But because it's moving at a high rate of speed away from the Earth, the flashes are only going to be seen on Earth every 12 minutes. All right, so it's going to take a longer period of time for those flashes to be received on Earth. And so when the spaceship moves away from the Earth, the flashes are spaced farther apart and they're seen less frequently. Instead of being seen every 6 minutes, now they're going to be seen every 12 minutes. Now, what are the ramifications of this? What does it mean for the astronaut, the twin in the spaceship, and the observer twin on Earth? Well, in this example, let's imagine that the spaceship moves away from the Earth for an hour and then moves back toward the Earth for an hour. All right. So what happens here is that as the spaceship moves away for the first hour and sends a flash every 6 minutes, the observer on Earth will see the flash every 12 minutes. Now, the ship turns around and is heading now back toward the Earth, but still sending flashes every 6 minutes. And so for the first 12 flashes, or I'm sorry, the first 10 flashes, right? Because if you're traveling outward for an hour and you send one flash every 6 minutes, that would be 10 flashes. So the observer on Earth will see the first 10 flashes every 12 minutes, but it will see the last 10 flashes as the ship is coming back toward the Earth every 3 minutes. All right, you follow that? As the ship moves away from the Earth, the observer will see 10 flashes 12 minutes apart. And as the ship moves toward the Earth, the observer will see 10 flashes at 3 minutes apart. So the ship is still emitting flashes every 6 minutes during a 2-hour round trip. During the first hour, it moves away from the Earth, and during the second hour, it moves toward the Earth. And so altogether, the ship is going to send out 20 flashes in that 2-hour period. Okay. Now, this is where it gets interesting, because in the end, what's going to happen is that the amount of time that the observer on Earth takes to see all 20 flashes is going to be 150 minutes. Now, think about this. For the first hour, he's going to receive, or the first 10 flashes, the first hour of the spaceship's journey, he's going to see 10 flashes every 12 at 12 minutes apart. That adds up to 120 minutes. For the second hour of the rocket's journey, the observer on Earth is going to see 10 flashes every 3 minutes, and that gives you 30 minutes. 120 plus 30 is 150 minutes, which is 2.5 hours. So the guy on Earth will age 2.5 hours. Now, in that same period of time, the spaceship is emitting 20 flashes at 6 minutes apart. Well, that gives you only an hour and 20 minutes, or 120 minutes, which is a 2-hour period of time. So the astronaut will live through 2 hours of time, whereas the observer on Earth will experience 2.5 hours of time. And so the observer on Earth will be older. The twin on Earth will now be older than the twin in the spaceship. Okay, let's look at this in a slightly different manner. All right, now in this particular example, what we're going to do is have a scenario where, again, let me move my ugly mug out of the frame here. So the now the observer on Earth, the twin on Earth, is going to send a flash every 6 minutes. Okay. With the rocket moving away from the Earth, the astronaut on or in the spaceship is going to see a flash every 12 minutes. Then he turns around and he flies back toward the Earth. The observer on Earth is still sending flashes every 6 minutes, but now the astronaut is going to see them every 3 minutes. Okay, so flashes sent at 6-minute intervals are seen at 12-minute intervals by the ship as it moves away, and at 3-minute intervals as it moves closer. A similar scenario to what we talked about earlier, but now the flashes of light are coming from the Earth to the spaceship. It turns out that the same time difference is actually seen now in this particular case. All right. From the Earth's frame of reference, all right, he's going to send out 25 flashes at 6 minutes apiece. All right. And in that case, it's going to take 150 minutes or 2.5 hours. Now, the first 5 flashes are going to be received by the astronaut. Whoops. Sorry. Are going to be seen by the astronaut in his first hour at 12 minutes apart. And then the last 20 flashes are going to be seen at 3-minute intervals for the last hour. Again, that only adds up to 120 minutes. And so the astronaut will experience only a 2-hour period of time, whereas the twin who remained on Earth will have aged 2.5 hours. All right. So regardless of which way we do this, in any event, the astronaut is going to be younger than his twin on Earth. This is the example that Einstein came up with to explain this idea of time dilation. Okay, so that, my friends, is the end of my little discussion of section 15.7. Your homework, which will be due at the end of the day today, is to do review questions 1 through 10 at the end of chapter 15. All right, I will upload those questions to the portal so that you have access to them if you don't have your textbook. All right, fellas, have a great day, and I will see you soon.